Yes. Okay, so okay, so you have a cable like that and a hinge connecting it to the ground. And you're given that the string, the rope has a length of 0.5 and it makes an angle of 45 degrees with the horizontal. And you're given that the coordinates of this point are 0.6, 0.5, 0.6, 0.4. And the coordinates of this point are 0.05, 0.2. And the first question is, I think if the tension in the cable is T, what's the force vector that's applied to that body by the cable? And then part B asks, what's the vector from the hinge to where the cable touches the wall? I'll call it the wall connection. Okay, so for part A, we're going to use two things. The first one is that any vector can be expressed as its magnitude times a unit vector in its direction. The cable tension is the magnitude of the force vector. So we know that this magnitude is just going to be this variable t. That's what it says. Okay. So now we have to come up with the unit vector. And there are two ways to come up with a unit vector. That's all we need now to come up with that force vector. Anybody have any questions about that idea? This is going to be a really important thing. We're going to use this in like every problem we do pretty much. This idea of breaking up a vector into its magnitude times its unit vector. So there's two ways to do this. The first way is if you're in 2D and given the angle the vector makes with some reference, you know, some reference line, then the unit vector is just going to be the cosine of this angle theta sine of this angle theta. The other way is if you're in 3D, and or you know starting and ending points of the vector, you know, end coordinates of the vector. Then you'll do it as like u is equal to b minus a, and then the unit vector is equal to 1 over the magnitude of u times the vector u. So those are the two ways to calculate that unit vector. And you see that all we have left to do is calculate the unit vector. So we know we're going to use one of these two. Well, this problem is in 2D. And we know that that force vector is acting away from the body along that line, along the line of the cable. That's what cables do. And we're given an angle between the direction of that force vector and a horizontal line, right? So we're going to use the first of those two approaches. Okay, so that's the one we want. And so now the way we're going to think about it is, here's our coordinate system. Our force vector is in this direction. And this angle is 45 degrees. So the unit vector is cosine of, it's 45 degrees counterclockwise from the positive x-axis to the vector. So cosine of 45, sine of 45. And that's 0.7071, 0.7071. And now we just multiply that unit vector times the magnitude t, and we get that the force vector applied by the cable is 0.7071 t, 0.7071 t. So what's the point of that? I said we're going to use this all the time. What does that do for us? Why don't we just represent that unknown force as an unknown vector, say fx, fy, and just calculate the two components? So what is the point? So we came up with that force vector. We expressed that force vector as 0.7071 t, 0.7071 t. Why didn't, what's the benefit of going through all that trouble when we could just write this as an unknown force vector from the start with like an unknown x component and an unknown y component of fx, fy? What benefit did we get from going through all those steps? You understand the question? We got a direction, so mathematically, I guess, what's the benefit? So yes, you're right that everything we did was right, and we can do it because we knew the direction for the cable. Mathematically, what's the benefit if we're trying to solve for like forces? What's the benefit mathematically of expressing it in terms of the unit vector instead of just two unknown force vectors? Yeah, you guys have an advantage. Yeah, this time you'll remember. Yes, it has to do with the number of unknowns. If you treat this like just a totally unknown force vector, you have to solve for two variables, the x component and the y component. Okay? To solve for two variables, you need two equations. Okay? once you go through this, if you know the direction, now we have that, even though it's a two-dimensional force, we have that two-dimensional force expressed in terms of a single variable. And so you only need one equation to solve for that. And being able to reduce the number of variables like that is going to be a key to solving almost every problem we do, because we're always going to be struggling with trying to come up with a way to express things where you have as many equations as you have variables. That's always going to be sort of the main challenge we have in these problems. Okay, so we went through all this, and what we did was cut down the number of variables by one. Okay, and then part B. So now what's the vector? So the vector we want is from the hinge to where the cable connects with the wall. Okay, so we want to figure out the vector that goes from here to the wall. That green is the vector we want. And to solve this, we have to recognize that that vector is equal to the sum of this vector and this vector. Okay, well, so I'll write this as, like, if I call this vector A and this vector B, and the green I'll call vector C. Then C, the one we're looking for, is A plus B. Well, A we can figure out because we have coordinates for those 2 points. So A is equal to the coordinates of this point, 0.6, 0.4, minus negative 0.05, 0.2. So that vector A is 0.65, 0.2. And that vector B, we don't know the coordinates at the wall where it connects, but we do know that it makes an angle of 45 degrees with the horizontal. So for B, I'm gonna set up the coordinate system. And we know that the vector we want is this. It has a magnitude of 0.5, and it makes an angle of 45 degrees with the horizontal. So that's counterclockwise 45 degrees from the positive x-axis. And so that vector B is 0.5 times cosine of 45, 0.5 times sine of 45, and that's 0.3535, 0.3535. Yes? Dang it. Okay, so this is positive and the 0.2 is negative. positive. Okay, and that makes this 0.55, and it makes this 0.6. And so now the vector that we want, C, is 0.55 plus 0.3535. So that is 0.9035 for X and 0.9535 for Y.